Hello and welcome to today's video. So on the workbench today we have the Nissan Leaf BMS unit. This is the one that I've modified. You can see my microcontroller is on there. And in the last video we were discussing possibly populating all of the I/O on here to be able to control everything directly from the BMS unit rather than using the power controllers. And I'm still leaning that way, and I think I've got everything figured out how I want to do it. So that's what this video is going to be. So essentially what we've got is we have an A stack and a B stack. So this will be 150 volts, 150 volts, and both of these guys are in parallel. And they'll actually be a whole nother set. So it'll be a C and a D off of the other BMS unit over there. I haven't modified the other one yet. So this is the only one that's modified. So what happens when you have a bunch of packs in parallel and say you have one cell short out, you now have the other three packs trying to charge the fourth pack that has a bad cell. So even if we can detect, oh hey, one of our cells is bad, we need a way to disconnect it from the stack to make sure that it doesn't get damaged. We don't drain the other packs. We don't try to charge it with the other packs. So that's what the power controller was doing. That's what this guy was doing to protect that. Originally, this was it read both sides of the battery pack, both sides. It was able to pre-charge, close the contactor, and read a current sensor. So it knew how much current was flowing in and out of the battery pack. So if it detected an anomaly, it would open up. We're essentially moving all of that code to this guy. So it'll be able to do everything. We're already reading. So this already had a sensor to read one side and another sensor to the other side, high voltage. We don't really need that because we can just add up all of our cells. We know the voltage for this, for A stack. We know all the cell voltage for B stack. So we know the total voltage on both sides. We will need a high voltage stack, 150 volt. Well, it would be like 200 volt to 0 to 5. So 0 to 200 volts in, 0 to 5 out, isolated for this, so that this can read the stack voltage. So it needs to know what the stack is. And then we'll pre-charge this voltage. We know this voltage. We know this voltage. We'll pre-charge up until they get close. We'll turn on the contactor, turn off the pre-charger. That guy's now connected to the main stack. We can do the same thing for this. So we pre-charge him into the other one. When the voltages get close, they should be really close, then the contactor will close, and boom. We now have both A and B stack on the main system bus, ready to go. We do the same with C and D from the other BMS unit. So that works out pretty good. We'll still have the two current senses, so each one has its own current sensor. So if something went wrong and maybe wire breaks and we noticed, hey, we've got current flowing out of this guy but not this guy, we can shut it down. We can do stuff, throw up error messages, whatever. Or if we've got an excessive amount of current going from one pack to the other pack, we want to disconnect that pack, right? We don't want to do that. So that allows us to facilitate that. So that's essentially what we're trying to do. Quick overview. Right? Hopefully that makes sense. Now, to help actually facilitate that, I went ahead and reverse engineered all of this. So I have the schematics now, or I drew the schematic for every component on that touches this connector. Well, except for the CAN bus, because I already know the CAN transceiver chip is it's this chip, and yeah, we already know what that is. We don't have to mess with that. We know it works. So one of the things is, while I was drawing this out, which is always good because I assumed these were N-channel MOSFETs, but if you take a closer look, they're not. So if you look at a normal like N-channel MOSFET, you have gate, drain, source, which is what that looks like. You've got the gate coming in here. We've got the drain. You can see the wire going out through this, or the trace coming out, going through this diode out to the pin. And then we've got ground over here on the source, because this is a sink drive. But the heat sink is also connected to ground. So if you put an N-channel MOSFET in there, it would just short. It would always be on. So obviously, these are not N-channel MOSFETs. The second clue is all of their MOSFETs have TR for transistor. So if you look, all of these is TR, TR25. They all have TR in them, TR8, TR28. But these guys are IC. Turns out these are not MOSFETs, of course. So these are intelligent. Well, I assume, I don't know what they actually were using because it's obviously not populated. I don't have one that has those in there. But I was able to find some that match the pinout. They happen to be, I think, 2.2 amps. And they are intelligent relay drivers. So they take care of everything. Inrush, overcurrent, undervolt lockout, like everything. They take care of all of it. Short circuit protected, you name it, they do it. So I was able to find both of those. And yeah, other than that, I think we're pretty good. The only other thing is, I think these pre-charge, or the ones that I'm going to use for the pre-charger, are also intelligent MOSFET drivers, because when I was looking for these, I found some SOT23 ones. And so I've got 150 milliamp intelligent MOSFET or intelligent relay drivers as well for the pre-chargers. So I think we're pretty close to what they originally intended, because it's pretty obvious that with the two contactor drivers here and the pre-charger here, this section that's not populated, yeah, I'm pretty sure that was originally intended to drive the MOSFET or the contactors in the pre-charger circuit. But anyways, so I went ahead and redid all that, or reverse engineered it all. And that is this schematic right here. So this is everything. Everything that touches this connector, except for the CAN bus. I actually ran out of room. And it's not in any particular order because this is just how I could fit everything on one page, because I didn't want to have it on more than one page. But yeah, so this is the pinout that I'm proposing here. So the only thing that I did is I repurposed the interlock circuit. It is no longer, I had to use one for my pre-charger, but well, I'll point that out when I get there. So essentially, we've got this is the actual logical pinout of the connector, and then this is the pinout that Nissan uses in their BMS document. I don't know why they're different, but they are. So, like I said, I don't have it's the CAN bus are on pins 12 and 24 up here, and I didn't draw that chip on there because we know it works. It's already talking over CAN bus. This board's been running code. If you watched one of the other videos, it runs, it reads all the cells already. So we've got, let's go through here. We've got contactor B, pre-charge B. We got our heater status, heater control. The reason I got that is this heater status, since we're running 150 volts battery stack and the heaters themselves are designed for 360 volts, I'm going to do a boost converter that takes to 150 to 360. And this heater status was if the relay was open or closed. And we're just going to report back if the boost converter is outputting 360 volts, we'll set that high. If not, then we'll set that low. So we can read the heater status. The heater will just be its own independent thing. If it gets 12 volts, or yeah, if 12 volts is sunk, the ground here is connected because it's a sync driver, then we'll turn on the boost converter and we'll take 150 to 360. So that's the plan anyway. We've got the spares are of course unused. I'm not using them for anything. There's some stuff that's multiplexed on different pins. I'll show that here in a second. So that kind of dictated how I ended up choosing what I did. But we got current sense B. We got some more spares. We got ignition status. That tells us if the car's on. We've got a charger status, which tells us if we're plugged in. We should technically know that over CAN bus, but it's kind of unique as either of those can power. So I can actually send, like if I hook up the charger status, I can actually power up the BMS with 12 volts if I don't have 12 volts available. So I don't know if I'm going to implement that yet, but the capability is there. We have the current sensor power, which goes to both current sensor A and B. And yeah, the one that says current sensor A is actually supposed to say current sense A, but I apparently didn't change it. And contactor A, and then we have 12 volts in, which powers the BMS. Like I said, if that 12 volts isn't present, I don't know why it wouldn't be. You can plug in, like maybe if the DC-DC converter's off, I can go, when you plug the battery charger in, 12 volts from that can actually power it up. So they're like diode-ORed, so it'll run off either of them. But yeah, anyways, so if we start over here, this is an A to D channel. Stack voltage sense, we've got some low pass going on, protection diodes, and then off to the A to D pin. Now, of course, 21 is also tied to this spare source, which will provide 5 volts, depending which 0 ohm jumper you, so we got a P channel and N channel. It depends on which 0 ohm jumper you populate, if you want it to come out 21 or come out 24. So I'm not using that at all because I needed A to D channels. So we got current sense B is over here. We got contactor B and contactor A, and this is that intelligent power or intelligent relay controller. It's a ZXM S665G is the one that I found that looks like it's the right pin out. They're rated for a couple amps, so that seems like that is the right thing for a contactor. We've got a spare input, which we're not going to populate. Another spare input, which isn't going to be populated. We've got the pre-charge A and B. A is the the sink for the interlock protection. I've repurposed it for this. It has a 2.2K resistor, which obviously will have to be replaced with something lower. I guess 10 ohms, but we'll see how much current it actually takes to turn on the pre-charge relay. I might do what I did on the power controller and use an essentially a solid state relay to do the pre-charge. Haven't decided yet, but I have the option to control the actual pre-charge relay. Although I don't think I have 4 of them. So yeah, work in progress. We have the heater output. That's the same as it was before. Like I said, this will actually tell the heater to come on, and it will actually turn on a boost converter to take 150 volts to 360 volts to run the heaters for the battery packs. What do we got up here? This is charger input, populated. This is like built in already. Ignition input, which again is also populated. And we've got this is a spare input, which was the original, not interconnect, what's it called? The original interlock circuit went in here. You can see it sourced 5 volts, and then this guy pulled it low. And then if you opened it, unplugged any of the connectors, high voltage connectors, it would read that, hey, I've got an open circuit. So that's all that's doing. So yeah, repurposed as a spare input because I don't have the interlock. I repurposed the interlock sync bit already. Then we got the heater input, like I said, for the boost converter to say, hey, we're working. And then everything else, we've got, this is our 5 volts for the current sensors. And then we have the A current sense, which this is the original current sense that was in the BMS, because it originally read the current sensor. And then we've got another spare analog input over here. And yeah, that's it. So that's a schematic. I'll pause there for a second so you guys can copy that if you want. But yeah, so that's where we're at with that. So that was kind of a long video, so I'm going to go ahead and move all this. Also, because I'm going to order all these parts, and I've had a couple emails now asking for PEC Sniffer 2s. This is the only one I've got left, which is the prototype one that I used for development, and I'm sure nobody wants that. So, same time, I will order parts to build up a couple of these. Let me know if you're interested in a PEC Sniffer 2. I can get more parts and build them up. Yeah, since we gotta wait for parts to come in anyway to finish this, we can go ahead and order everything all at once, and then possibly also need parts for this guy that I'm working on. That'll be the next video. So anyways, yeah, thanks for watching. Bye.